Okay, so welcome everybody. My name is Sylvain Gigant. I am professor at Sorbonne Université in Paris, and I will act today as the president of the jury. So before we start, I just want to introduce quickly the member of the jury. So we have two reviewers. So Jean-François Giovanelli, professor at the University of Bordeaux 1. And on Zoom, we have Professor Simon Harridge from University College London. And then two examiners, so Thierry Blu, from Professor des Universités at the Chinese University of Hong Kong, also on Zoom, and myself. And then we have the two thesis advisor and co-advisor, so Françoise Perrin, who is a directrice de recherche at INSERM here in Lyon, and Nicolas Ducrot, who is a maître de conférence at INSA here in Lyon. Okay, so we are now ready to start. So Antonio, you have about 45 minutes-ish to present your work, and then we'll follow up by the discussion.
Thank you very much for this introduction. So welcome everyone, and thank you for being here for my PhD defense on single pixel imaging, compressed video acquisition, and reconstruction using deep learning. So first of all, let me introduce the motivation for my thesis. This thesis was funded by the Harmony Young Research Project that aims to provide imaging tools for fluorescence-guided surgery. So fluorescence-guided surgery, the classic framework for fluorescence-guided surgery is that we use optical filters to acquire the image to the right, and this is what the surgeon sees. And essentially, what we can see here is the signal of the protoporphyrin 9. And with this map, the surgeon can then excise the tumor tissues. Now, the issue with this method is that it can be reasonably inaccurate. So in order to solve this problem at Creatis, there has been work conducted that utilizes the full spectrum of the protoporphyrin 9 molecule in order to accurately detect tumor tissues. And the issue with this approach, however, is that there is no spatial resolution. So ideally, we'd like to have a method that combines both approaches, meaning a two-dimensional image alongside with an accurate determination of the tumor tissues thanks to the analysis of the spectrum. So in order to achieve that, we need a hyperspectral camera. So if we take a look at the hyperspectral imaging techniques, what we can see is that if you take a look at hyperspectral cameras or spectral cameras that produce three-dimensional images, the third dimension being the spectral one, we can see that as the number of spectral channels increases up to 200 channels, the cost also increases up to $100,000, and this becomes prohibitively expensive. So if we also take a look at point detectors, such as a spectrometer, what we can see is that we can have about 10 times as many channels in the spectral dimension. And what we can also see is that the cost is also about 1,000 times, 100 times lower than high-end hyperspectral cameras. So ideally, what we'd like to achieve is a hyperspectral camera with spectral resolution of a spectrometer with a cost similar to that of a spectrometer. And since the spectrometer is a point detector, we're taking a look at the single pixel camera. Now, the single pixel camera is a device that can produce two-dimensional images. It only uses a digital micromirror device and a single point detector alongside with a set of lens. The idea of the digital micromirror device is an array of small mirrors that can be tilted independently. And these mirrors can be organized in certain patterns. And what happens is that we form the image in the DMD plane, and then the light that hits the mirrors on the on state are then reflected to reflect the light through the lens that are then gathered into a single point detector, which allow us to compute the measurement of the the inner product of the object, so of the image of the scene, and the pattern of the DMD. So we can store this value, and obviously then we can change the pattern in the DMD and acquire another measurement. From these measurements, we then can use a reconstruction algorithm in order to recover the two-dimensional image. In order to turn this into a hyperspectral camera, what we can do is that we can replace the point detector with a spectrometer. And in replacing the point detector with a spectrometer, instead of recovering a measurement vector, we recover some spectra. And from these spectra, we can then use a reconstruction algorithm to reconstruct the three-dimensional hypercube. This is the setup of the single pixel camera that we've been using at Creatis throughout the thesis. And we have, so essentially the light comes from here. We form the image on the DMD plane through a telecentric lens. Then the light is reflected through to a relay lens that, and then it all converges into an optical fiber that's connected to a spectral analyzer, spectrometer. So let's move on to the objectives of the thesis. We aim to recover single pixel image, hyperspectral single pixel images, to acquire and recover hyperspectral single pixel images in real time. And we aim to apply this to data from an experimental single pixel camera. So let's move on to the state of the art in order to understand what is done in single pixel imaging, what are the limits of those methods, and that will guide the rest of the contributions for the thesis. So the first implementation of the single pixel camera was essentially a hardware implementation of the theory of compressed sensing, where they would acquire images at sub-Nyquist frequencies, and they would use random patterns alongside with a sparse representation of the image, and then they would recover the image with an L1 constrained optimization method. One of the issues with this approach is that it's time consuming to solve the L1 optimization problem. So another popular alternative to that is simply acquiring measurements in an orthogonal basis and then apply an inverse transform to recover the image. So this has been done for the Hadamard basis, for the Fourier basis, and the wavelet basis, for instance. As far as hyperspectral single pixel imaging is concerned, it has mostly followed the trends of single pixel imaging as a whole. So the first implementation of a hyperspectral single pixel camera by Magalhaes was following the theory of compressed sensing, and then further implementations, such as the one from Rousset, have essentially used downsampled basis scan. And then in 2018, Higham from the University of Glasgow proposed a deep learning framework for single pixel imaging, where they interpreted the single pixel acquisition model as the encoding part of an autoencoder, and then they would train the measurement patterns alongside with the reconstructor, which gave them this kind of pattern, and the performance of their reconstructor would outperform the other state-of-the-art methods. So let's take a small look at the limits of these approaches. So for fast single pixel acquisition, we need to acquire downsampled measurements, meaning we need less measurements than the number of pixels in the image that we aim to recover. And we also need low integration times, which usually leads to very noisy data. So the inverse transform approach usually gives us an easy to interpret reconstructor. It's also fast, however, it may suffer from downsampling artifacts, and it can be susceptible to noise. The optimization-based methods, such as compressed sensing or total variation, are easy to interpret as well. They can be robust to noise, but this leads to time-consuming algorithms that may have regularization parameters that we may have to tune for each image. And deep learning gives us fast reconstructors, good quality of reconstruction, and but the problems is that it can be susceptible to noise, and it leads to solutions that may be hard to interpret. So we will focus our contributions at trying to find the best, a good compromise between all of this. So ideally, a solution that is easy to interpret, robust to noise, that is fast, and that gives us a good reconstruction quality. So before we move on to the contributions, let's talk about the general framework under which this was conducted, since there was a certain number of choices that were made throughout the thesis that have guided the rest of the contributions. So we chose to acquire the measurements in the Hadamard basis. So the Hadamard basis functions are binary, which is an upside when it comes to the TMD and the speed of the TMD. It's about 100 times faster than if you had grayscale patterns. It's mostly made up of vertical, horizontal stripes and also squares of different spatial frequencies, which allow us to recover vertical details, horizontal details, and diagonal details. And it has good noise reduction properties. It has fairly good compression ability. However, one of the problems is that it has negative values. So we have to, so in order to implement them, we have to first acquire the positive values, then the negative values, and then we make the difference between both of them, since there's no such thing as negative photons. In terms of the forward model that we have in a noiseless case, we have the downsampled acquisition of the image in the Hadamard domain. And we have chosen a mixed Poisson-Gaussian noise model. The Poisson distribution models the photon noise, and the Gaussian distribution models the electronic noise. And the Poisson distribution is parameterized by the image intensity and photons. So as the number of photons goes up, the noise goes down, and as the number of photons goes down, the noise becomes more important. So our goal is to estimate the image F given some noise measurements, M alpha. In order to illustrate this, let's take a look at this example. So if this is the image, and this is the image in the Hadamard domain, here we take the downsampled image in the Hadamard domain, and then this is corrupted by Hadamard noise, and from this, this is corrupted by mixed Poisson-Gaussian noise, and then from this noisy measurement vector, we aim to recover F, which is a no-closed inverse problem, and we choose to reconstruct F as the conditional expectation of the image given the measurements. So let's move on to our first contribution, which is neural network architecture based on denoising and completion methods. So if we train a neural network J with weights theta to minimize the mean squared error, then our estimator is approximating the conditional expectation of the image given the measurements. Now, when we take a look at the framework from Higgin, so what we had was a fully learned reconstructor where we had two parts, first a measurement to image mapping and then an image to image mapping. The measurement to image mapping was done through a fully connected layer with a lot of parameters and that can be fairly hard to interpret. So in order to solve this issue, we have chosen to replace the fully learned, fully connected layer with an analytical formula. And since our reconstructor aims to compute the conditional expectation of the image given the measurements, we have chosen to start with to interpret this measurement to image mapping as the estimator assuming that our data is Gaussian and noiseless, which leads to the following solution in the Hadamard domain, where we essentially just keep the acquired measurements and then we estimate the missing measurements from their correlation with the acquired measurements. And then for general data that isn't Gaussian, this solution is not accurate, but it's still the best linear unbiased estimator. And in order to solve the fact that the data may not be Gaussian, we use the convolutional layers to regularize the Gaussian solution. This does not work on noisy data, so we need to take a closer look at the noise model. So since we have differential measurements, our data is corrupted by a mixed Scalam-Gaussian noise model. The Scalam distribution comes from a difference of two Poisson variables. And then we derive the likelihood of the data. And what we get by through the convolution of the two probability density functions is that we get an infinite sum of a product of exponential functions with Bessel functions of the first order. So this has no closed form expression. There's not much we can do with it. So in order to circumvent this problem, we've chosen to approximate the Scalam distribution by a normal distribution with a covariance matrix that is diagonal and where the terms of the diagonal are signal dependent. And once we've got this noise model, we can then once again get our conditional expectation assuming Gaussian data, which leads to Tikhonov regularization, and which in the Hadamard domain is fairly easy to solve since we first denoise the acquired measurements and then we estimate the missing measurements through their correlations with the acquired missing measurements. And these two equations can be interpreted as layers of a fully of a neural network. So this leads to the following algorithm where we first denoise the acquired data, complete the missing measurements, and then we get our image through the inverse transform, and we regularize this in the image domain. We've applied this to data from our single pixel camera, and we've compared our method, PCNet, with total variation, Tikhonov regularization, and the fully connect deep learned, the fully learned reconstructor from IGN. And what we got is here is the ground truth, and this is the fully sampled noisy image that we downsample in order to recover these images. We downsample for several compression rates, so 12% to 25%. And what we can see is that the proposed method gives us better contrast, so it's more robust to that Poisson to that mixed Scalam-Gaussian noise. And we also see that we have less of these grid-like artifacts that appear from the downsampling in the Hadamard domain. So, to conclude this contribution, we've chosen to interpret the measurement to image layer as a Tikhonov regularization problem, which adapts to the level of noise automatically, and we also estimate the missing details of the image, and then we follow this by an image domain regularization done only on already regularized images. So that means that our image domain layers are more robust to noise. And this is ideal for experimental grayscale and hyperspectral data. And we'll talk a bit more about hyperspectral data soon. In terms of communications, we've done a conference proceeding from ISB 2020 and a journal paper on Optics Express 2021. So let's move on to our next contribution, where we will generalize this to hyperspectral data. So our motivation is that hyperspectral data usually has varying noise levels from band to band, and that depending on the wavelengths, we will have more or less signal, and the less signal we have, the more noisy it'll be, and conversely, the more signal we have, the less noise we'll have. So we need a reconstructor that has that adapts to the level of noise, which is why we thought that we could apply the proposed DC net method previously presented in order to reconstruct the images, since it adapts to the level of noise, and we could do that independently for every channel. However, this would not exploit spectral redundancy. So as we can see throughout the different spectral channels, what we can see is that the details of the images tend to be similar, and this might be exploited. So we proposed the following framework, where we first denoise and then complete the missing measurements, and then we stack these. We do that independently for each spectral channel. Then we stack them into a hyperspectral cube, and then we apply 3D convolutional layers in order to regularize this across the spectral dimension. If we take a look at some results from our hyperspectral single pixel camera, we can see the 3D regularization versus the 2D regularization and the Tikhonov regularization on a per channel basis for different channels, and then the pseudo RGB image. What we can see is that the 3D reconstructor reduces the levels of noise, so it regularizes fairly well and reduces this kind of noise. We also see that in terms of the pseudo RGB image, the ground truth is red with a slightly orange hue, whereas the Tikhonov regularized image is more of a darker red, and the 2D approach of denoise completion method has a much more orange hue. So this means that both of these methods are a little bit far from this one. However, and the proposed method is a little bit closer. It's also red with an orange hue. So on that front, we have a little bit of a better color ratio. We can also see that in terms of the girth of the branches of the star sector, we have a little bit of, we have thinner branches with the Tikhonov regularization here, for instance, thicker branches in the with the 2-dimensional approach, and with the 3-dimensional approach, we have branches that are very similar to the ground truth. So to conclude, we've extended the denoise completion approach with Tikhonov regularization for hyperspectral data. In order to regularize across the spectral dimension, we've applied 3-dimensional convolutions, and we've successfully applied this to data from a hyperspectral camera and also grayscale data. In terms of communications, we've published a paper on Optics Express in 2021, and we've also done a proceeding on SPI 2020. So now let's move on to the third contribution, which is a deep learning reconstruction method that uses the expectation maximization algorithm. So so far, we've seen the image layers as a post-processing step, which fails to interpret accurately the solution, where we just see the approximated reconstruction image as the output of the neural network. So in order to solve that, we'll try to link this with traditional reconstruction algorithms that in particular compute the maximum a posteriori. This can be, the maximum a posteriori can be, for instance, solved by the expectation maximization algorithm. So if we take a look at the expectation maximization algorithm, we create a sequence of images such as the posterior distribution is non-decreasing. We use a hypothetical vector called X of complete data, which essentially has all the data that we've acquired and that we haven't acquired. So in our case, this can be interpreted as the image in the Hadamard domain, a noisy version of the image in the Hadamard domain. And in order to acquire our measurements, we simply downsample the complete data, and that gives us the measurements. For Gaussian noise and any general distribution of F, this leads to the following two-step algorithm, where first of all, we have a Tikhonov regularized solution, and then we have another solution that involves the probability density function of F of the image. But since the probability density function of F is unknown and we have no analytical formula for that, what we can do is that we can replace this formula with a deep learned reconstructor and hope that instead of having an analytical expression of this, that through exposing it to samples of images, it'll eventually be able to regularize correctly and learn what it needs to learn from the density function of F. So this leads to the proposed algorithm, where we first denoise the applied measurements, then we complete the missing measurements through their correlation with the denoised measurements. We do an inverse transform, and then in the image domain, we regularize thanks to this neural network. So this offers a generalization of the previously proposed denoise completion approach. And we've trained the neural network in an end-to-end fashion, meaning that we've trained it alongside with these equations. And for a fixed number of iterations, meaning that we choose an algorithm that we'll only use for a certain number of iterations. In our case, it's 4 or 5 in order to be fast. If we want to visualize this algorithm, so here we have the image, the applied noisy measurements. We take the previous iterate, and then we denoise the applied measurements. We complete the missing measurements, and finally we do an inverse transform, and then we regularize across the image domain. In order to properly test that the proposed method has an interest, we've chosen to take a neural network for the image domain that is fairly small, and that way we can compare it to neural networks with more parameters in order to see if there was an interest in that. And so what we've done is that we've compared our proposed method with a unit, which is a well-known architecture in deep learning with many more parameters than the proposed network. And we've also compared it with the standalone neural network with the architecture shown in the previous slide, alongside with the total variation. And we've done that for different noise levels and different compression rates. What we can see is that the proposed method is better at regularizing the solution and getting rid of artifacts induced by the Gaussian, the scaling noise. We can also see that we're capable of retaining some details that are somewhat smoothed out with the unit reconstructor, and we have a better patch of grass than here. In terms of PSNR metrics, we've computed this over the testing set of the STL10 database, and we've done so for different noise levels and different compression rates. What we can see is that for a low number of photons and a lot of noise, the proposed method is better in terms of metrics, much better than the others for some compression rates. And for a high number of photons, what we can see is that we're slightly better in terms of metrics, even if not by a very large margin, we're still better. So it seems that the proposed method is working well. If we summarize this, we've proposed a deep learning method based on the expectation maximization algorithm. This offers a generalization of the Tikhonov mapping proposed previously with, and we can also see that even with lower number of learned parameters, we're still we still have a good performance over several noise levels. In terms of communications, we've done an ISB processing, and we've also submitted a paper to IEEE Transactions of Computational Imaging. So now let's move on to the final contribution of this thesis, which is a Kalman filter video reconstruction framework for single pixel imaging. So the motivation is that so far we haven't really exploited the natural redundancy of videos over time, meaning that when we acquire videos, through the different frames, most of the information is kept through over time, and this can help us because maybe if we use the correlation over time, we can then acquire less coefficients and use the information from the previously acquired frames. So we've chosen this update model for the different frames, where the future frame is essentially explained by the previous frame, and the differences are due to some noise. In order to get our linear estimator, we can just apply the Kalman filter, which computes the conditional expectation of the image given the data for time series. It essentially has two steps. First, a prediction step where we try to predict the future frames from the previous frames, and also where we try to estimate the noise variance from the previously acquired covariances. And then there's an update step where we acquire the future frame and the future covariance based on the acquired measurements and the previously predicted frame, and we do some Tikhonov regularization over those two parameters, which incidentally also solves this optimization problem. So if we apply this to a toy example that we've crafted ourselves, so we're going to apply it to this example of a white spot on a black background moving to the right. And for the first frame, we'll always estimate the first frame with 12% of the measurements of the image, and then we'll acquire the rest of the frames with 5% of the measurements. So here we have what we call perfect Kalman, where we essentially have the perfect update model that we know because we've handcrafted this model. So this is not the case generally speaking, but here we can use it just to understand what's going on. And then there's the Kalman filter, where we assume that the future frame is very similar to the previous frame. And then we have a Tikhonov regularization with 12% and 5% of the acquired measurements. What we can see is that on the Kalman filter, we have these ghost-like artifacts that happen from the first frame, and these artifacts are essentially reducing the image quality to the point where even the case where we don't consider the previous frames is better than this case. So this is a problem. We can also see that in the case where we perfectly know everything, well, in that case we perfectly know the forward model, the reconstruction with 5% of coefficients is very similar to the reconstruction with on the first frame. So let's try to understand where these artifacts come from. So as we said previously, where the update step of the Kalman filter solves this optimization problem. And if we consider a simpler case where all of the covariances are essentially a regularization parameter times the identity. In the Adamar domain, this means that we are essentially taking the acquired coefficients and regularizing them with respect to the previously acquired coefficients. And if we haven't acquired the coefficients, then we just keep the same coefficients from the previous frames, which explains why we have this problem of artifacts that remain from the first frame. So this means that we need to consider a sampling scheme where we sample the coefficients that have changed the most over time and that we are least certain of, which is why we're going to try to sample the coefficients that have a higher predicted variance. So in order to do that, we train a neural network to compute the variance of our linear estimators. Since the perfect Kalman filter gives an image reconstruction of the similar quality to the first reconstructed frame, we can try to do that for the first reconstructed frame and then apply the same method for the other frames. So we can train a neural network to reconstruct the variance of this linear estimator, the one of the first frame. And what we can do is then just feed this to a neural network, and that gives us a bigger neural network that we can train to minimize the mean squared error with respect to the standard deviation. And this allows us to get an estimate of the variance. We can see here the results that we get. So this is the ground truth image. This is the first frame acquired through Tikhonov regularization. And then we have here the deep learned variance estimator, which is very similar to the true variance estimator. At least it allows us to estimate where we are least certain of our coefficients. So if we implement this if we summarize the proposed method, so what we do is that we take the previously predicted frame, the previous frame, we try to predict the new frame, then we apply our neural network to estimate the variance. We select the coefficients that produce the highest variance, and then based on these coefficients, we can choose the new measurement patterns. We acquire the measurements with these patterns, and then we have our measurement vector with which we do the update state from the Kalman filter. And so we've tested it on our toy sample once again with the same exact perfect Kalman or exact Kalman, the same Tikhonov regularization using 5% of the parameters for the future frames. And then we have the Kalman filter, where we assume that the future frame is essentially the same as the previous frame, but where we assume that we know the true variance. So, so this one right here. So this is not what we will have in if we try to image things correctly. And this is what we have with our deep learned estimator. We will compare these two in order to see what the limits of the method are, even if we assume that we perfectly know everything. So what we can see is that we no longer have the remaining artifacts from the first frame. And we also see that the different spots are moving correctly, and we have a very similar type of spatial resolution as the one on the perfect Kalman filter. However, what we can see is that after 10 or 15 frames, we have some artifacts that happen from the model drifting that this is not the true model of update. We don't know what it is, but it's not this one. So we're still capable of discerning good estimation for 10 frames. So this is the conclusion for this section. We've proposed a time-adaptive sampling scheme that allowed us to reduce the number of acquired measurements from 12% to 5% for 64 and 64 images, where we were still capable of retaining more or less the same reconstruction quality over time. And however, after approximately 10 to 15 frames, there were some artifacts that appeared due to the model drifting. So that was one of the limits. And let's move on to the conclusion for this presentation. So in terms of our goals, we aimed to develop reconstruction algorithms for real-time single pixel imaging. We aim to apply them to hyperspectral imaging and to have an interpretable solution that is fast and that adapts to different noise levels. In terms of contributions, we've developed architectures based on Tikhonov regularization and the expectation maximization algorithm. These methods denoise the measurements and estimate the missing measurements into Hadamard domain, and then we regularize the image in the image domain through convolutional layers. So this allowed us to have models that adapted to noise and that were fast and with good reconstruction quality. And in order to further reduce the number of acquired measurements over time, we've proposed a time adaptive acquisition scheme for Kalman filter-based reconstruction. And we successfully applied this to experimental data from a hyperspectral single pixel camera. In terms of limits, our algorithms were tested on 64 times 64 images. So images of higher resolution may be needed in order to be able to apply this on for surgery purposes. And the dynamic model for the Kalman filter leads to some artifacts, which means that in order to solve these problems, there are some perspectives to take into account. For instance, a patch-based approach may be helpful to increase the size of images, and we could use generative models from video prediction tasks as predictive models in order to reduce the artifacts over time. And we could also use RGB single pixel camera hybrids for bimodal image reconstruction. The publications throughout the thesis are the following. We had 2 published journal papers, one submitted journal paper. Our softwares and datasets are online, and we've also had 5 international conference with proceedings. Thank you very much for listening, and if you have any questions, feel free to ask.
Perfect. So, okay. So we'll now move to the Q&A, and we'll start by Jean-François Giovanelli here. So the idea would be that you want to maybe say a few words in French,
yes,
before moving to the Q&A.
yes, I would like
please,
to give my first general comments in French, and then switch back to English. Je voudrais vous remercier, l'encadrement, et je voudrais remercier la structure de m'avoir proposé de participer à l'examen de ce travail, mais surtout vous remercier vous pour ce travail. J'ai trouvé votre présentation tout à fait intéressante. J'ai trouvé qu'elle était bien structurée, qu'elle était pédagogique. On suit bien le fil de vos développements et vos quatre contributions majeures. J'ai trouvé que c'était intéressant. Un autre choix aurait pu être de sélectionner 1 ou 2 ou 3 de vos contributions majeures et puis d'aller un peu plus en détail. Vous avez fait un choix différent, il est tout à fait rationnel, tout à fait recevable. Du coup, on va peut-être creuser un peu certains détails dans la discussion. Et un petit mot sur le manuscrit. Hein. J'ai trouvé aussi le manuscrit tout à fait bien écrit, tout à fait bien construit. J'ai écrit que je trouvais qu'il y avait quelques éléments qui étaient un peu superflus. Voilà, c'était pas nécessaire. Voilà, ça pouvait avoir pour effet de délayer un peu les choses au lieu de focaliser vraiment sur vos contributions. Mais comme je l'ai dit et je le redis ici, j'ai trouvé que c'était un très beau document et un très beau travail et donc une très belle présentation. Ok. Voilà ce que je voulais dire de général. Je vais essayer de re-switcher in English. So maybe we could have a look at slide number 9 and 10. I would like to have some additional information. Yes. Can I have a look at 10? Yes, number 9, please.
Number 9.
Just could you give me some details about these plots?
Oh.
So the first one on the left and then on the right. Can you comment that?
Yes. So so this is they use their hyperspectral imaging system to image this type of lead. So this is not the reconstructed image. This is the lead that they showed in their first contributions in their paper. I believe that they didn't actually show the reconstructed image of the LED. But they did plot the estimated spectrum of the lamp, and they compared it to the hypothetical one. So what we see here is the reconstructed spectrum of this red LED. What they reconstructed with.
And can you comment about the two peaks, the large one and the small one? What does it mean? With respect to wavelengths?
Well, so there's one big peak at around 630 nanometers and another one at 650. So I mean, this means that we've got a red light, which is fairly accurate with respect to the LED that we can see in the image. But it's also, I think this was also interesting in that it showed that we were able to have very high spectral resolution with this type of system, since we were able to discriminate peaks that are separated by about only 20 nanometers, which is not the case for all. No, I don't. I'm not sure.
And the second.
Yeah, this one.
Yeah.
So this image was done from a phantom. From this phantom actually. And so they showed the reconstructed image at different wavelengths. So what we can see is that at 525 nanometers, they would reconstruct the green part of the phantom. And at other wavelengths, so for instance, 625, we would reconstruct the other part, but not the green part. So this was the application of a basis scan for this type of phantom. Yes.
Kind of hyperbolic regulation parameters in the inverse transform in one sense, or maybe in the deep learning. Can you comment that? For example, in the deep learning, you have to select things that can be associated to regularization parameters or some tuning of things in the method, and maybe also in inverse transforms.
Yes. Well, the inverse transform is it does not have regularization parameters. It only depends on the type of transform that you've chosen. From that point of view, it's kind of transparent. In terms of learning,
Excuse me, for the inverse transform, if you do not have regularization parameters, it means that the transform is invertible. The transform is invertible.
yes. Oh, yes, of course.
And
sorry.
in a steady, in a stable way.
Yes.
Maybe we could have some situations where we have an inverse transform, but that can be sensitive to noise and requires a kind of stabilization, a kind of regularization, a kind of
Yes.
parameter to stabilize, to make it.
Yes. I agree. I mean, here we all considered mostly orthogonal transforms, which is the
Okay.
one. And well, yes, it can happen. In which case, I would obviously, if we have to regularize the first transform, at that point, I would probably. I mean, if I had to put it in the box, I would probably put it in the box closer here to the green box. I would put it closer to the optimization-based methods, but
Okay. Yeah.
that would be mostly my choice. But because this one refers to orthogonal transforms.
Yeah. Okay. So that's fine. And then regarding
for learning, yes, there's a certain number of hyperparameters. Well, even the reconstruction architecture is, in a sense, a parameter in and of itself. There's also the fact that, well, I didn't really put it here, but usually we also add a regularization term across the parameters of the neural network. So yeah, there's a lot of choices in terms of hyperparameters for deep learning. What I meant when I didn't put regularization parameters, that once we've chosen the hyperparameters, we no longer need to touch them in order to reconstruct an image that. Once they're chosen before the training, and once we have trained the reconstructor, we no longer need to touch them, and we just use it as a reconstructor.
Yes. So my next question is in relation with optimization-based methods and regularization parameters. And for example, some of the results you give, for example, in slide 22. Yes. In that case, for the TV reconstruction and the Tikhonov reconstruction, you need to tune hyperparameters. So my question is, how did you tune them?
Yes. So in terms of Tikhonov reconstruction, we've applied this one. So the one where we use as a noise covariance the one that's signal dependent. In terms of the parameters sigma 1 and sigma 2 1, sigma 1. So this was acquired through a covariance matrix that we computed in the Adamar domain through an image database. So we took an image database, took the inverse transform, the Adamar transform of the images, and then we computed the mean, we computed variance, and then a covariance matrix, sorry, and then we used those matrices to acquire these coefficients. So that's for Tikhonov regularization. For total variation, we had a parameter, a tuning parameter for with respect to total variation contribution, optimization problem. We manually tuned it for the different images there.
Okay. And of course, for the deep learning approaches, you have an set of examples, and to learn your network, the parameters of your network. And then what about using the same set of examples to tune the Tikhonov or the TV approach? I mean that for TV and Tikhonov, you need to tune things, and whether you tune it by hand or on an example set or set of examples. And then you also have a set of examples to learn your nets. So what about using this, the idea of using the same bodies, the same set of examples to learn the network and to tune TV or Tikhon off to make comparisons maybe more convenient or more fair or something like that?
So if, let me rephrase the question to see if I understand it correctly. What you're saying is that we could use an image database to try to find the tuning parameters for the total variation,
Yes, for example.
for example. And the same for Tikhon, so using an image database to
And using the same image database.
yeah. So well, this is essentially what we've done for Tikhonov regularization when we computed the covariance matrices here. So it's already what we do for Tikhonov. For total variation, we have not done this, obviously. Could we have done it? Let me.
For example, by computing the total variation of the images of the database, or something like that.
Yeah, maybe we could have. Yeah, probably.
Okay. Okay. Yeah. Okay. Nice. Now, with the about the computation of the solutions, the slide we have just seen before with the matrices and so on. And I also have the same question regarding the Kalman approach. Regarding computations, matrix and versions and so on, how do you compute that? For example, sigma sub 1 minus 1. Do you compute that, or you solve the system, or you use kind of Cholesky decomposition?
Yes. So, well, equation 18. So we took a diagonal approach, meaning that we're only working matrices. So this is actually easy to compute in the fast way, and we need to do this for every time for different images, since the amount of noise depends on the measured signal. So for every measurement vector, we need to compute a different covariance matrix for noise, and therefore this one we need to do on the fly, but it's fairly fast, so it's not really an issue. For this one, since we've pre-computed the covariance matrices, what we did is that we inverted it once and for all, and then we just applied search, because we could obviously try to use solvers, linear solvers, but one of the issues is that the reconstruction time may depend on the for every time it's solved. And generally speaking, we can just compute this previously, and then once we're done, we just need to compute a matrix product vector, which is fairly.
And this matrix does not depend on parameters, on noise level, or
no, the noise level is
only this one.
Yeah, it's all concentrated on sigma r.
And sigma 1 is free from regularization parameters.
Yes.
Okay. So regarding these kind of aspects, I have a question about slide number 17, and it is also mentioned in your document in chapter 3. I have a question about the expectation that is here. When you introduce the idea of autonomy, that is the estimate, J of M in your document, you mentioned a criterion that is minimized by through the function G, that is an expectation of G of M minus F, and there is an expectation.
Yes.
And then you mentioned that the deep learning approach replace, in one sense, the expectation by an empirical mean.
Yep.
That is given here. But my question is, this empirical mean involves a set of m sub I, f sub I, means that a known, it means object and corresponding data. So it could be in relation with an expectation with respect to both the joint law of the object and the data.
Yes.
In your relation in chapter 3, and maybe in Annex C, the conditional mean theorem, I think something is unclear about the probability distribution under which you consider the expectation. The expectation here seems to be the posterior expectation, the expectation of the posterior distribution of the unknown object given the data.
Yes.
On the right, it looks like an expectation, and as a joint law, it joins including data and object. Because on the right, you produce a summation with various objects and various set of measurements. So it is an approximation of an expectation with respect to the joint law for the data and the object. And in some of your expectation, it seems to be expectation under the posterior law, given the data. So I think something could be clarified here, or maybe I missed something. Can you comment that?
Sure. You want clarification with respect to the minimization of the expectation with respect to certain.
In fact, my question is not really about the minimization of the expectation.
All right.
It's about the expectation itself. The expectation,
yes,
is an expectation with respect to a probability distribution.
Yes.
My question is about the probability distribution. It seems that here we have an expectation in relation on the left, in relation with the posterior distribution, object given measurement. It seems it is also the case at the beginning of your chapter 3,
okay,
arg mean and so on. The expectation seems to be under the posterior law. And on the right, it seems to be under a joint law.
yes.
So,
well, the thing is, we have samples, so that means we have sort of a set of samples M and F.
yeah,
So we have samples not from the distribution F and M or M and F, but we have the joint distribution.
yeah.
So from this joint distribution, we can actually compute estimators of F and M and M and F, I believe.
From this set of examples, M sub I, F sub I, you can compute this loss function
Yes.
and minimize it with respect to theta. That's the job of the learning step. Okay. So implicitly, it is a joint law, a set of corresponding M sub I and F sub I. I can say in a different way, across the examples, the data changes and the objective changes.
Yes.
That's fine. That's a job of learning based on a set of examples. Okay. From a theoretical standpoint, what you write seems to be an expectation under another law, another probability distribution. Because you write something about a probability distribution for object given $1, and not a joint distribution for object and data. In the theoretical part, when you minimize and when you derive the MMSE, the minimum mean square error, and then you have the partial expectation. But okay, maybe we could, you can think about that. And
yes, to be perfectly honest, if I don't have a board or something like that, I might actually struggle to understand the question accurately. So
maybe my question is also unclear. No problem. Thank you. One or two questions. Okay, I also have some questions about maybe slide 32.
33, that's 32, yes.
And maybe when you compare results between Tikhonov and Kalman filter and yes, maybe something.
Yeah.
Yeah. Okay.
Or maybe
yes, this one.
Okay.
In fact, you have when you consider the Tikhonov approach, you define a quadratic criterion that include probably a kind of smoothness of the object through derivative, a quadratic norm, squared Euclidean norm of a derivative, spatially and across time. And you have a kind of large quadratic criterion.
Yes.
And then through the Tikhonov approach, you try to minimize this criterion, including all the images through time.
No, because well, we do every frame independently.
Okay.
So we don't regularize through time. One of the reasons why we don't do that is because first of all, as the frames, as we keep having more frames, we'll have to regularize over more data, which is a little bit of an issue, computationally speaking. And another reason why is that we just want a quick constructor for every frame, so it's actually much faster to just take the Tikhonov regularization that we presented here in order to reconstruct these images over time. So
and you regularize through time based on state model of the Kalman filter.
Yes, yes.
My question was, in fact, a question about Kalman filter and Kalman smoother.
Okay.
And then the relation between Kalman filters, Kalman smoother, and the criterion that is minimized through the Kalman filter. But
yes, I understand. So the Kalman smoother, yes, regularizes several frames in a would regularize several frames in a row, as opposed to the Kalman filter that just computes one frame at a time. So we haven't applied a Kalman filter method either. We've only limited ourselves to the Kalman filter. Yes, we might have been able to apply it.
or maybe a fixed log or something with a kind of sliding window to include
showing through previous grades, but
to take advantage of one frame
Yes. Well, the
from
thing is,
past and some future.
yeah. So I think that's useful if you don't mind having the delay for real-time applications. It might actually be delayed by 2 or 3 frames, and since each frame might take about 0.1 seconds, which would be looking at a significant delay in terms of visualization. But it could be applied. Maybe it clashes a little bit with the goals of the thesis, which was real-time imaging, so that we can see in real time what's going on through the hyperspectral camera.
Maybe one last question regarding uncertainties. In the Kalman framework, or maybe in other frameworks, and more specifically about neural networks, how could we have information about uncertainties, variances, error, probability of errors, and so
on? Well, it depends. I guess it depends. So if we're capable of achieving the full Bayesian inversion, for instance, we have a probability density function, and from this we have a perfect characterization of the solution with all the uncertainties we want. Since that's not necessarily possible, we're limited to point estimators. So when we need 2 estimators, point estimators, if we want to characterize the uncertainty, we have to choose the estimator and then this estimator. We need to choose an estimator that accurately depicts the uncertainty environment. So we mostly use in this part the variance because it estimates how much we diverge from the estimator. So we quote unquote characterize the uncertainty through the variance, which is not entirely accurate, but it is what it is when full inversion is not possible. If we had, which is why we used here deep learning to estimate the variance. We can once again use the same type of approach that we use for conditional expectation, but for conditional variance, and so on and so forth. This type of approach was compute control is the point estimators of variance for several uncertainty estimators.
Okay, thank you. So that's okay for me. Thank you very much.
So yeah, thank you, Jean-François. So we now move to the second reviewer, who is on Zoom, and who is Professor Simon Harridge. So Simon, the floor is yours.
Good morning. First of all, thank you, and Antonio, for a very interesting thesis. I enjoyed reading it. I think you've done many interesting advances in the ideas of compressed sensing and Bayesian estimation and hyperspectral and dynamic imaging. Congratulations. In fact, already some of the questions I was thinking of have already been asked, so I will perhaps be a little briefer. Maybe we could start with 1 or 2 general points. If we return to your motivation in slide 11, where you talked about the approaches inversion, inverse transform optimization, and deep learning. So one of the ideas that deep learning is that it gives you the reconstruction at a faster rate without the need for the optimization based approaches which are slow. I wonder if you thought about using invertible networks, which allow you to effectively exactly invert a transform that you learn, rather than simply minimizing a loss function. Have you considered those at all, or have any comments about that?
No, I didn't really consider that kind of approach.
Okay, that's fine. I mean, it's possibly an alternative that might have a little bit of extra performance. That's quite an interesting topic currently in use of deep learning and inversion. Okay, maybe you could say a bit more then about. I was pleased to see that you used an approach where you combined Poisson and Gaussian noise.
Mm-hmm.
As you explained, yes, that's great. Thank you for that slide. As you explain here, your Poisson variance is the image intensity, so the same in the classic Poisson model. Can you say a bit more about the scaling between the Poisson and Gaussian? So here you have the variance of the Gaussian, but are you always just summing this, or is there an additional weighting between those two noises?
No, we're always summing these. Well, the weighting is usually done through the mean and the variance of the Gaussian distribution. So there's, yeah. So what we usually do is that we estimate this for our detectors through several measurements and analyzing the data with those measurements. And once it's done, we just keep it as it is and do the reconstruction assuming this.
And have you found that that's a reliable model across different image intensities?
We found it reasonably reliable in that. So I'm going to take this just to illustrate, but this is obviously these are two different channels, so it's not exactly the perfect illustration for that, but it's going to be similar to this. So what we did also, like empirically, just to see if it seemed to work, is that well, first of all, we through this image we tried to estimate all the experimental parameters. And once we had the experimental parameters, we took the image that we integrated over long periods of time that had little noise, and we tried to apply the parameters and see if we got something that looked somewhat similar. And most of the time, we did see something very similar. That when we corrupted the noiseless image with the Poisson-Gaussian noise model, we would found things that looked similar. Obviously, we didn't come up with any type of metrics to estimate this or anything like that. We just did a visual assessment, and based on that visual assessment, we were pretty pleased with that model, so we kept it as it was.
Okay, thank you. So my next question was in connection with chapter 6, and so I think in the slides, if we go to slide 25.
No, 25. Yes. Okay.
Oh, sorry. Wait a minute. Next slide.
Oh, yeah.
Yes. Sorry. Yes. So I think you were mentioning about that you do the channel by channel denoising before using the multispectral
Yes.
stack. Can you comment why you did that? Because another approach would be to directly use a correlation in the measurement domain and to do a fully 3D cross-channel denoising directly before the unmixing step.
Well, I guess the choice that we made was the one where we did it on a per channel basis. Where on the measurement domain we chose to work on a per channel basis, simply because it was simpler and it was very fast. But yes, we could have tried to regularize across the spectral dimensions in the measurement domain as well. Yes.
It depends whether you think the noise would be correlated. If you think of it as purely Poisson, you normally would not talk about the correlation in the Poisson measurements, but with the mixed model, there might be correlation.
Maybe. So, well, where is it? Yes, with this mixed model, what we don't really say here is that the parameters of the Gaussian distribution depend for each channel, and each channel is kind of acquired by different detectors. So, and I believe we made the hypothesis that it was how should I put it? That it wasn't correlated, and I think some papers that I read on that also made that hypothesis and said it was a reasonable hypothesis. So we just kept it as it is. Chose to say that it wasn't correlated, but we haven't really fully delved into that question when doing this study.
Okay, but the results are impressive, so I think it's justified by the performance at least. Okay, so moving to chapter 7, where you look at this unrolled iterative method.
Mm-hmm.
So you mentioned this is trained end to end, so you have the complete model. So you need to fix the number of iterations. Is that correct?
Yes, it is correct.
Yeah. There are some ideas about how to use a sort of unfixed iteration number in these iterative optimization methods. For example, did you use separate weights in each iteration, or did you use weight sharing?
We used weight sharing. The reason for that was simply that we wanted networks that weren't very that didn't have that many parameters, and that were how should I put it? And that were easier to load on a graphics card and so stuff like that, in order to make the application even faster and closer to our application. For out of curiosity, we did try through different not sharing the weights over the several iterations, and we found out that it didn't really have a huge impact on the performance compared to the added complexity. So it had some impact, but it wasn't that big, and so we chose to simply share them across the iterations.
Okay, I think I would agree. It doesn't make a large amount of difference, and it does make sense. But roughly, how many parameters have you got? What's the dimension of the learn space?
So in this neural network, if I recall correctly, we have roughly 20,000 parameters. 28,000 parameters, something along those lines.
So that's relatively small, actually.
Yes.
So that shouldn't be too onerous in training, even if you did use separate weights. I would have thought.
Yes. No, it's not really the training time. It's more about having lighter neural networks that were already storing these matrices here, which can take up some space. So the more we minimize the memory resources, the better.
Yeah, sure. Do you use a full matrix representation, or are you using like a low rank approximation for those covariances?
No, we're using a full matrix representation of this matrix. Like, we don't keep sigma 2 1 and sigma 1 and then we invert sigma 1. So like we compute we pre-compute sigma 2 1 and sigma 1, and then we pre-compute this product and this inversion, and then once it's done we store it, and then we don't touch it any longer.
Did you look at the spectrum of that matrix to see how fast it decays?
Excuse me?
Did you look at the spectrum of it, the eigenvalues, to see how fast it decayed? Because often it, could be fairly well represented by a low rank approximation, perhaps.
I did not, but I did take a look at the conditioning of sigma 1, and it was reasonably high, so I just kept the approximation as it was. I just kept it as it was, and didn't touch it anymore.
Okay, thank you. So if I turn to the Kalman filtering work, so I also had a similar question about the smoothing possibility, but I won't ask that. I of course, using a smoother would not be compatible with adaptive changing, and which I think is a key in the finding of your research. Just a small point. Where was the slide? 47.
47. Yes, here.
Can you just explain about this capital F, the linear predictive matrix?
Yes.
I don't think you mentioned actually what you use for that.
Yes. So, well, this is a toy example. So, the way we fabricated this toy example is that we created the first frame, and then I computed a permutation matrix that essentially moves every pixel to the right. And that's how we got this toy example video. And so this permutation matrix is actually F. And with this permutation matrix, we computed all the in this example we used it in this model. So instead of having f of t equals f of t minus 1, we have f of t equals f times f of t minus 1. Right. At which point we do all the Kalman filtering equations and we recover the big F here.
But why aren't you learning an estimate of that?
Oh, well, why we're not learning an estimate of that? How should I put it? Generally speaking, we did find that we took a video database, and we estimated how accurate this model would be, and we actually found it to work better than when we actually tried to estimate a linear estimator for general videos. So generally speaking, we found that this linear model was the best we could come up with, but maybe we missed something on that front. Anyway, we weren't really capable of finding a linear estimator that was significantly better than the identity.
Okay, thank you. So there's a final question, a little bit looking to the future. So you've shown with your studies in compressed sensing, well, the hyperspectral imaging application, which is one of the classic ideas, also dynamic, which is another one. What do you think are the prospects for doing what's sometimes called, well, not well, a dynamic hyperspectral, so combining multispectral with time variation. How would you approach such a problem, and what do you think is a reasonable expectation?
Well, so yes, I see what you're saying. Well, it's not an easy question because obviously regularizing across 2 dimensions is hard. With respect to single pixel imaging, I guess to single pixel hyperspectral imaging in particular, I guess I guess even just reconstructing parallelly the different spectral bands with time approaches, such as this one, for instance, could be of interest. In particular, because how should I put it? In particular, because this spectral regularization allows us to pick up the information on the less noisy channels and then try to interpolate that into more noisy channels. So the hyperspectral regularization could be of interest to circumvent the problems due to noise. And the temporal regularization, at least for single pixel imaging, in my opinion, could be used for in order to try to go faster in that, try to exploit the information over time and try to predict where to find the pixels, the coefficients of more significant value. But I don't think I can give a much better answer than this. That it's a challenging problem, and I'm not sure that it's easy to do so in real time. If we're talking about realistic, well, at least not now.
Okay, I think that I'd probably agree with you there. Although, I mean, the possibility exists for having, a second order of magnitude of compression. That might be the appealing idea behind it. But yeah, I think nobody has really addressed this in a very thorough way yet. So maybe a possibility for the future. Okay, that completes my questions. Thank you.
Okay, you are finished. Sorry.
That's right. Yes.
Yeah, he was finished, right? Yes.
Yes, he was
Okay.
finished.
So thanks a lot. Sorry, I was not hearing very well you, but okay. So we now move. Thank you very much. So we now move to the first examiner, who is Thierry Blue from Hong Kong. So Thierry, the floor is yours.
So can you hear me? Is it okay?
Yes.
Okay, I'm not completely sure because I'm a bit far away. Okay, so first, Antonio, thank you for your presentation, which was very fluid. Okay, so for me, it was the rhythm was very good. And okay, for the written documents, I should say that I have not read everything. I'm sorry, but what I have read, showed me that you see it was you pay attention to details. You see, mathematically it looks very nicely done. Okay, it's not only LaTeX. Okay, it's the notations, etc. So you see, I think it's you see, at least it looks like a very good work. Another thing is that the subject of your thesis is very interesting from my point of view. Okay, being able to reconstruct a full image, you see, based on 1 pixel, even if it's a problem. Okay, I know from those people in you see at Rice University, okay, Baranyuk, etc. So still, okay, I was interesting to see a kind of motivation, okay, for that type of problem. A biomedical application, okay, in particular. Okay, so for the few things that I have read in the, and actually that you said also in the thesis, because I have worked a little bit on Poisson noise, etc. So you were saying that when there is less signal, there is more noise. Okay, so this is exactly the contrary. Okay, for Poisson noise, what happens is that if you have less signal, if you have zero signal, actually you have zero noise. So this is something that I'm telling my students, and I'm showing them actually that you see when there is no signal, you have something completely black. Okay, whereas if you have Gaussian noise, okay, you still have something there, right?
Mm-hmm.
So it just to say that of course what is right is what is correct is to say that the signal to noise ratio increases. Okay, when you have more photons. Okay.
Yes.
But it's not really that the noise decreases, the noise increases actually. So, but that's not, you said it does not mean much. So there is something I was a little bit wondering, okay, you did not use any variance stabilizing technique for dealing with Poisson, because this precisely has the good property of somewhat separating a little bit the noise and Poisson and the signal. So
yes. So
why didn't you use any stabilization technique?
Yes. So yeah, we are aware of yes, variance stabilizing transforms, such as Oscom transforms and all the derivatives from that. Okay, so one of the reasons we did not choose to apply that type of transformation is because the variance stabilizing transform stabilizes the variance, but it does not stabilize the mean, which it's okay, but considering that we're using deep learned estimators, we actually want to stabilize the mean. Stabilizing the mean ensures that
I'm not sure I understand what it means, stabilizing the mean. Of course, you see the transformation is nonlinear, so it modifies the mean value, okay, in a nonlinear way. So is this what you mean by stabilizing? Or?
Well, I mean, okay, so what we feed a neural network are normalized images where the mean is normalized and where the mean of the measurements is normalized. It's a bit of an issue to feed to a neural network samples that have different different orders of magnitude for the mean, and that can happen when we apply variance stabilizing transforms. So that's why we chose not to apply any variance stabilizing transform. I don't know if I've been clear.
Yeah, well, you know, I can guess slightly, but okay, it's not. I'm not fully convinced. Another thing is okay. Then in your document, when I looked at what you were doing when you were, for example, using kind of maximum likelihood, or you see a technique like that. You were always simplifying to a Gaussian probability. Okay, so at least assuming that, for example, in the case of Poisson, you have enough photons so that it's Gaussian.
Mm-hmm.
At least what I know is that the Poisson likelihood you see you see the log likelihood is nice in the sense that it's convex. So you see there is no big issue in minimizing, you see, especially if you have a regularization term that is also convex. Mm-hmm. So I'm just wondering if you have considered, you see, being a bit closer to, let's say, the true, you see, in particular in the case where you have a few photons. Okay, I'm not sure if this is a situation that may be encountered, but this is where I see that you may need to consider a likelihood that would fit better.
Well, maybe if I can here, can explain a little bit more in detail why we did this kind of approximation. So, since what we measure is actually an inner product in and on itself, so there's actually several contributions. So we integrate over the whole image, essentially. And that's why for the aimed applications, even when we have a very low number of photons, so for instance, 2 photons per pixel, which is very, very low, even in these kind of applications, we're still somehow above the kind of 20 or 30 threshold in terms of acquired value. So that means that we usually are making a reasonable approximation because we're usually above 20 or 30, which at which point this approximation isn't too bad. So for the aimed application, even for a low number of photons, the approximation is still reasonable. At least that's what we believe. But yeah, maybe for other applications that this might not be quite as suitable.
Okay, no, it's just it was just a comment more than you see a complaint. Okay. So now there is something you said. I'd like to understand a little bit. You are limited in speed by the frequency of the DMD, the switching of the DMD, right?
Yes.
Even if you have you see a deep neural network that is at the speed of light, okay, you still need to. So I saw a number which was 20 kilohertz for your DMD. Am I right, or something like that?
Yes. Yes.
Okay, so I think you can have faster than that. I think in my lab we have 50 kilohertz, something like that. But okay, this is a limit. So does that mean that? So I understand that for this reason you have considered relatively small images. Okay, so 64 by 64. Mm-hmm. But there is something I don't understand very well here, because you are using compression ratio that are between 5% and 12%, if I understand well.
Yes.
So this means that you are aiming at relatively, you see, below the second, below the tenth of a second, probably even faster than that. You see you see at least acquisition of the scalar product that you are interested in.
Mm-hmm. Yes.
But it's a little bit less convincing, because the images that you show are really quite coarse. Okay, and. Yes. I was thinking, especially if you mention biomedical applications, you may need significantly more pixels. So I think it would have been more convincing if you had been able instead, you see, to focus on a large number of pixels, but still very compressible, actually much more compressible, for example. You see what I mean? That is to say, images that would be a little bit simple in the sense, let's say, I could simplify by saying, okay, just a disk or whatever, you see. So something you can compress like by a factor 100, you see. So very few scalar products, and being able to reconstruct with, you see lots of details, you see this silly circle, you see disk, would be actually more impressive in terms of, so I'm just, you see, wondering a little bit, because you see, when I was seeing your percentage of compression, which was okay around 12%, I was thinking, oh, but usually when you use JPEG, you have at least you see 1% or something like that. So I was thinking, yeah, those it's not very competitive. Then I tried myself, you see, on MATLAB, just to see what it would look like on a 64 by 64 image. And okay, I buy what you are doing, but I mean, it's not very demonstrative in a sense. You see my point?
Yes. So the images are, yes, I mean,
that is to say, you could acquire, you see, maybe a slightly more scalar products, okay? but still being within the second, and be able to demonstrate, you see, not high resolution, but you see what I mean, something that looks like natural normal resolution. So that's a comment I wanted to make, you see, because it was somewhat you see contradictory to, you see, a little bit too synthetic. Okay.
Well, I mean, it depends on the type of approach that you're aiming for. I think there's a couple of limits that that have to be said about what you just said. So comparing this to JPEG is not a fair comparison for several reasons.
No, I agree with you. It's just a number that I have in mind.
Yes, but the thing is, JPEG obviously uses it uses two things. It uses obviously the discrete cosine transform, and then it uses small patches, and it does the compression over the small patches. This is not something we can do. That wouldn't be reasonable to do for us, in the sense that doing the compression over the small patches means that in terms of implemented patterns, we would only have a small patch of tilted mirrors. So that's a bit of an issue, in that we would be even more, we would have even more, an even worse signal to noise ratio with respect to the Gaussian noise. So our data would be a lot more noisy. And another thing where the comparison with JPEG is not really something that we can do is that JPEG actually does things the other way around, in that it knows the images, so it knows where to seek the coefficients, whereas we actually need to acquire coefficients because we're blind before we acquire the coefficients.
No, you misunderstand my point. Okay, I'm saying JPEG simply because of the 1%. Okay, but one thing that that can easily be done, you see, is just take you see the lowest frequencies. You see, so you don't need to you take scalar product with let's say the lowest frequencies Hadamard basis. Okay. And I'm pretty sure, you see, if you have an image that is much larger, okay, that's 10%, or you see, is really, you still have a very good, you see, reconstruction. My point is, you see, not to compare with JPEG, but more to say that you could have tried to show maybe simpler images, okay, simpler in the sense that they are, yes, simpler, you see, to see, but at the same time, they would have a higher resolution. When I'm saying a disk, okay?
Like this. Images like this, for instance, where we have a circle and...
yeah, but something like 512 by 512.
Oh, okay.
you see my point? It's I'm pretty sure that if you use total variation, minimization on something, you see where you have you see compressed sensing on very few scalar products, you still reconstruct quite nicely the disk. Okay, you know the examples that Candace has given on the you see the Shape-Logan phantom. Okay, so it's a bit artificial, but these are you see. Not large images, but reasonable size. And still, and now the compression ratio would be much more than certainly, let's say 5% or 12%, you see. So what I'm saying here is that you are fighting with a data set, you see, 64 by 64, that is not going to be very demonstrative for you see, especially if you go to see, you see the biomedical people. But you see, so then my question would be, is there a limit that is also, you see, that comes from the other side? Because here I have mentioned only the DMD, but you see, very likely also the neural network may need also a little bit more work, should I say. So I'm not sure exactly if you can comment on, you see, working with larger images, even if they have much less you see information content.
Yes, so to be perfectly honest, we have shied away from simpler images like this or the Sheplog and Phantom images like that, simply because, I mean, the total variation is actually perfectly suited for those examples, but they're not like, but it's not suited for more complex images. So if we wanted to apply this to several different images.
Yeah, actually, I'm happy that you show this this slide, because I'm a bit surprised for the performance of the total variation at 12% here, because you know, my experience with total variation is to obtain something super flat. You see, so it's something that you can you see that changes with the the regularization parameter. So I'm
yes.
just wondering.
Yes,
You see if yeah,
yes,
how,
sorry.
yeah, maybe you can comment, you know, on how you chose your regularization parameter for
Yes,
to obtain this result.
I'm assuming you were expecting images like this, maybe that are a lot flatter.
Yeah, something like that. Yeah.
Maybe I believe this image was obtained. I also tried to tune it manually, but I did it according to the PSNR rather than through visual, because obviously I tuned it manually. So it depends on how I perceived things at the time. I think this was tuned in manually as well, but here we did it visually because it was experimental data. So I just took a look at the images and thought, oh, this one looks better than the other. That's how I tuned it, because I don't really like computing metrics on experimental data. It can be a little bit challenging, and the metrics are very hard to interpret. Whereas here it's on simulated data, so I actually computed. I actually took the image that gave me the best PSNR out of the images that I had, and that's how I got this one. So I just took the best PSNR, and it just so happened to be this one. So that's the image that I got to tune the regularization parameter. Maybe I could have regularized more in terms of choosing the parameter.
Yeah, I would certainly expect something, you see, especially given that the original image, apart from the Chinese character on the top, you see, apart from that, it seems that the image is really flat, you see, in terms of intensity. So over a large number of pixels. So I'm surprised that you see tuning a regularization parameter, you see at a larger value would not give something nicer, but okay.
Yeah.
Okay. Well, you know, I don't have so many questions. There was you see one, but it's probably in relation to the one that the Ridge has Simon, sorry, has asked. You see, it was more. You see, if there was the possibility to simply approximate, you see, the solver using a neural network. Okay, so approximate, for example, total variation or whatever the solver that you are using by a neural network instead of you see implementing you see the solution that you propose. But okay, you have already somewhat answered the question negatively that you did not consider this option. So okay, I'm fine with that. Yeah, so this is all I have, I think. And but it's you see, I realize that it's a lot of work, so I congratulate you for this this big effort.
Thank you.
Thank you.
So thank you, Thierry. Okay, so I will now ask a few questions before I give the floor to the supervisor. So first, I really want to congratulate you on the quality of the manuscript and of the presentation. So I found the manuscript extremely pedagogical and didactic. I mean, I'm more of an experimentalist, and I know mostly the compressive sensing part, but I enjoyed reading the rest, and I think you made a good job of really explaining the concept in a simple way and your results. I also really like some of the aspect, let's say scientific aspect, like this approach to really globally solve this hyperspectral reconstruction, not just spatial and spectral, but globally. I think that's good, and I think you say somewhere that it's a first in this context of the.
Yes, it's not something that has been studied extensively.
Okay. And of course you really have this approach to use deep learning, but in an interpretable way, and I think that's also my philosophy. So I think I really support this approach. So it's really commendable. I just have a few maybe relatively general question, and one is about almost philosophical. So in compressed sensing, you use L1 minimization, and you want to know what is the basis on which the object is sparse, where you look. And in this approach, you do first a minimization, like an L2 minimization, for instance, typically with this inverse reconstruction, and then you pass it through the neural network. So can you maybe comment a little bit on the pros and cons of the two approach in terms of, so let's say, where is the L1 minimization? How does which part deal with the sparsity? Can you maybe comment a bit on that?
Yes, so I guess the L1 minimization is a very, very specific framework in that from the acquisition to the reconstruction, everything is done in order to do L1 minimization. And if you want to apply any other type of reconstructor to that kind of to those measurements, it wouldn't quite be suitable. Yes, it all comes down to the famous sparse representation. I have found it that sparse representations are never truly sparse for all images. I mean, there has been some work with wavelets, some learned dictionaries, and so on and so forth, but it's never totally sparse. So the first hypothesis that's made is never truly correct. And even then, it's one of the issues I found. One of the philosophical issues that I found with L1 regularization is that it works perfectly if you have no noise, but if you have noise, then you know that you can maximize the error with respect to some constants that we don't know. So when you apply it, it's not really that helpful compared to this. The chosen approach with the L2 regularization, the Hadamard, is very linked with the acquisition of the Hadamard domain to us, at the very least, because one of the big advantages of the Hadamard transform is that we can take details on several scales. So, for instance, we can acquire the coefficients on a low level. And then if we realize that, oh, we have more time, we want to change the pressure, we can just change it on the fly however we want. Whereas that's not true to take random patterns. So I believe the framework that we've used allows for more flexibility in terms of acquisition and in terms of adapting over time to the number of measurements and so on and so forth. So that's what motivated our choice to shy away from L1 regularization, move on to the proposed approaches.
Okay, and maybe just also again a relatively general question. So your approach. So now you've tested the algorithm on numerical data and experimental data that you downsample to fit the 64 by 64, if I remember well.
Yeah, well, yes, for our experimental data, what we do is that we acquire all the coefficients in the Hadamard basis, and then we simply get image in the Hadamard basis. We just do an inverse transform, and that gives us the image. And then, in order to apply this to experimental data, what we could do is we just take what we acquired, the fully sampled image of the atom domain. We just forget about, say, 88% of the coefficients, and then we do our reconstruction.
Okay. And so what would you miss in the experiment to really, let's say, not say to the clinic, but to a real sample? So what would you need to do? And do you think it will be ready for that already, or?
For a real sample, I mean, then again, it just depends on the quality of the reconstruction that we see. I mean, yes, it can be applied in real time. We are working on an experimental setup that does that in real time. That doesn't sample everything and then doesn't sample, right?
But you mean you're working also with systems which also have the when you can put a real scene in front of the design, or
Yes.
That's already what you have.
We haven't reached the point where it works, but I know that I'm not the one working on that, specifically, but I know that we're working on importing this into a clinical microscope. Obviously, it's not to the point where it works yet in the clinical microscope, having issues with signal, so on and so forth. But yes, we are working on that.
Okay. Okay, maybe a quick last one, and which is about the hyperspectral work again. So you have this global approach, which is really good, but to some extent you don't have explicit. I mean, you're still measuring the NMR basis.
Yes.
Right. So which means that in the sense that you're not sampling the spectrum in a smart way. Because you're still measuring all the wavelengths.
Yes.
So could you imagine whether there would be some ways to kind of take into account this sparsity? I mean, also the fact that there is maybe a known spectra that you're interested in that maybe you can know a priori. Would that fit into this framework?
I'm not sure that I understand the question.
Well, if you look at a specific sample, like in a medical domain, you would probably know beforehand what kind of spectra you have.
Yes.
Would that be something that you could plug into the algorithm in some way, or at the training stage, or what? How would you take that into account?
It's something I would be reluctant. I mean, it could be plugged, but I would be reluctant to plug it into an algorithm. The reason for that being that I would much rather get an image and then compare to the theoretic spectra of protoporphyrin 9, for instance, in order to, when we compare, then we can see if we can more accurately determine if it's cancerous or not. Whereas if we use the information of the spectrum as a prior, I'm afraid that we might add information that might not be true and might lead to some artifacts that we don't want. So I would be reluctant to do so, but it could be done.
Okay. Okay. Thanks. Okay, so I will stop now. Thank you again for your work and your presentation, and give the floor to Nicolas, I believe. So yeah. So be careful, because I'm not sure. Yeah, if you connect. Yeah.
Mute. Okay, should be okay. Thank you. So as we have already had long and fruitful discussions, so maybe I won't ask questions, but I can comment on the background of the PhD. So this PhD was funded by a young researcher ANR project, whose objective was to demonstrate the relevance of single pixel imaging in image-guided surgery. So as you nicely showed in your introduction, and in particular, the goal was to apply single pixel imaging to fluorescence-guided surgery, which is routinely used by the surgeon. And as single pixel cameras can be coupled with spectrometers, so we can build hyperspectral images with very, very high spectral resolution. And this is what we're interested in, because with this high spectral resolution, you can tell the difference between the tumor tissue and the healthy tissues. And that's really what we'd like to do. But obviously, we have to first design the experiment. So this is something we've been working on. So Antonio showed you or a system that was the previous version of the system, and we have a new version of this hyperspectral camera that has still to be coupled to the surgery microscope. So this is ongoing. And the goal of the project was, and Antonio's project was in particular to speed up the acquisition by reducing the number of measurements and also speeding the reconstruction. So Antonio contacted us for a master project. It was in 2018. So at that time, our idea was to estimate the motion of the sample using a few frames, and then to use that knowledge of the motion to acquire the next frame. So we're working on in a wavelet basis at that time. And Antonio was rapidly able to understand the problem, run the experiment. He implements different algorithms and analyzed the results. And as the project was progressing well, we also proposed him to collaborate with other colleagues to work on a matrix factorization problem for single pixel imaging, which led to an SPIE proceeding. So in summary, we've been quite impressed by his work and the scientific maturity, and he did very well during this internship. So we encouraged him to apply for a PhD, which he did, and this is why we are here today. So Antonio started the PhD in October 2018. So at that time, it had become quite evident, even more evident, that the deep learning methods were maybe among the best to solve inverse problems. But what I would like to underline here is that we had like limited experience in the field of deep learning when we started this project. And once again, Antonio did a very good job and was able to produce rapidly results, implement solution in a short amount of time. So that was very impressive. And well, yeah, I really enjoyed his ability to formalize problems. I think he has a quite strong mathematical background, and I hope also that was quite apparent in his presentation. So he has had a good level of productivity, let's say, with several conference proceedings. So two SB proceedings, two SPIE proceedings, and two published paper in Optics Express as first author, and also another paper submitted to IEEE TCI. So this one is in review now. So good productivity, but okay, what I would like also to mention here and to underline is it's his programming skill, but because he was also really involved in the development of okay, it's here, so of the Spirit package. So this is a PyTorch-based package that we're developing in the lab for image reconstruction. And he was really the one who like built the core modules of Spirit. So thanks a lot for also involvement in this activity, because this is very useful in the lab to have like tools that we can reuse also after the thesis, and like write tools for the community. So that was good. Okay, and well, apart from the technical side, let's say, I would like to say that it has been really a pleasure, Antonio, to supervise your PhD. Antonio has also really good like human relationship, and he works hard and he has a critical eye. So I think he has a bright future, and so I would like to wish you the best. I would like also to thank all the jury members who come here, read the reports, and participate to the defense. Thanks a lot for your good comments and suggestions. So I was taking notes because it was really interesting. But I think maybe we should continue that over the lunchtime because yeah. Okay. So that's it for me. Thank you again, Antonio.
So thank you. So Françoise.
Yes, thank you. So I will also only make comments, and my comments are nearly the same as those of Nicolas. But first of all, thanks to all the jury members to have accepted to join. Some are here. We are very happy to welcome you in Lyon, and some unfortunately are far away. So I would say that also I would like to congratulate Antonio for the presentation and the last version, and it was very, very comprehensive and well illustrated. So about the context of the PhD, I would like to add that Nicolas has initiated this project on single pixel imaging in Creatis. And I think that it's very interesting because it has a lot of perspective nowadays, either for biomedical imaging more oriented in the clinic as is foreseen in this Harmony project, or even in microscopic imaging. And what is interesting also is that we see that even in other domains, not in optical imaging, but in X-ray imaging, there are also similar trends to do things of this kind. So I think it's very promising, and that in France, there are still very little work on this topic. So I think it's an original project. So about the first PhD in the lab related to that was the one of Florian Rousset. And then Antonio, you went and go pursue the works of Florian. And also, yes, in your first slide, there was a work of Laure Alstom, who in another team did something on multispectral, but not imaging, multispectral measurement. So finally, you joined, you had a topic in relationship with these two previous PhD, but you did a lot to do hyperspectral single pixel imaging and even ideally video hyperspectral imaging. So it's an interesting topic, and of course you were very well involved in the field of deep learning and what can be done with a deep learning method. So I would also say that I was also impressed by your ability to do mathematics and to formalize the problem, and you are very interested in deriving some demonstration. And what is interesting is that you have a good physical sense of the maths, and it was clearly apparent, I think, in your presentation that you give an interpretation of the formula. So it's not just math for math, but you have an interpretation of the formula, and then you can propose new method with still some physical background. Despite of that, you also were a bit involved in the experimental setup. So also it was not your primary interest, but you could take some experimental data and process experimental data. So this is also very good. And as Nicolas said, you spend a lot of time in programming. So you program in PyTorch, and you were quite an expert in the lab with PyTorch. And so this could also help other students, and you also teach at INSA, and also you give a TP, a practical in the deep learning spring school organized by LabExtreme. And I agree that it was very pleasant to work with you. You are always in good mood, nearly. Only once I could tell a small story. I saw you a bit discouraged is when with Nicola, you discovered that there was a little tiny error in your program, and yet that you had to redo all simulation for the CCI paper. So this is the only time I saw you a bit low, but you did it and you overpassed it. So congratulations, yes, this work has led to many publications, and we hope that the one in revision in IEEE TCU will be successful. And then thank you, and I hope you will be able to continue what you want to do. Thank you.
Okay, thank you very much. So we went around. If there is no more question, I suggest we go to the deliberation phase. Are we staying here?